in today's problem, we're going to be heating 2 kilograms of water from an initial temperature, T1, of 20 degrees Celsius to a final temperature of 100 degrees Celsius. So boiling. That's a temperature difference of 80 degrees. The specific heat capacity of water at 20 degrees Celsius is 4,182 joules per kilogram Kelvin. Likewise, at 100 degrees, the specific heat capacity is 4,210 joules per kilogram K. Now the average of these two, we add them together and then divide them by 2. So that equals 4,196 joules per kilogram Kelvin. So the formula we use to find out the energy transfer required to go from 20 degrees C to 100 degrees C is Q, which is energy transfer, which is what we're looking for, times mass, or Q equals mass times specific heat capacity, and final temperature minus the initial temperature. So now we go ahead and plug in our numbers. So we've got a mass of 2 kilograms, times that by our average specific heat capacity, 4,196 joules, times our temperature difference, which is 80 degrees. Therefore, our energy transfer is 671,360 joules. Or you can write that as 671.4 kilojoules. Now, to put this in practical sense, say this is a jug of water at room temperature 20 degrees, and there's 2 kilos of water in that jug. Now what happens if we decrease the amount of mass in that jug to see if that affects our efficiency? So say we drop it down to 0.5 kilograms of water. So we've already got the mass, the specific heat capacity, the mass, and the temperature difference. They all stay the same. So basically we can just plug in our new mass into the equation. So that becomes our Q is what we're looking for. So 0.5 times 4,196 times 80 degrees. That equals 167,840 joules of energy. So we can see there that the energy transfer is directly proportional to the mass. So how does this affect your electricity bill? First, we need to understand that electricity is measured in kilowatt hours. So 1 watt of energy equals 1 joule per second. So, because it's over it's in kilowatts. Let's say we have 1000 watts times 60 seconds times 60 minutes. That's because it's in hours. Now, that leaves us with 3,600,000 joules in 1 kilowatt hour. So in scenario 1, where we had 2 kilograms of water, so our kilowatt hour, we had 671,360 joules. Now we divide that, because it's in joules, we divide that by the 3,600,000 joules, and that equals 0.1865 kilowatts per hour. So that's the first scenario with 2 kilograms of water. So in our second scenario, where we had 0.5 of a litre, we had ended up with 167,840 joules. Divide that by our 3,600,000 joules per hour equals 0.0466 kilowatts per hour. Now, to work out what this would actually cost you, say to boil that jug, the difference between having 2 litres in there and 0.5 of a litre in there, you need to know what you're being charged per kilowatt hour. Say on average we get charged 35 cents per kilowatt hour. So we just go ahead and we multiply each of these by our kilowatt hour charge out rate. So times 0.35, because I'm doing it in dollars, times 0.35. Just plug that in and find out what it costs. So that equals 0.065 of a dollar, which equals 6.5 cents. And this one is 0.0163 dollars, or 1.6 cents. So you can see the difference there in what it costs. It's almost 4 times more expensive when you're trying to boil a full jug of water as opposed to just boiling what you need. I hope this helps.